Hi friends, we left over here in our last video. We discussed Heisenberg's uncertainty principle, and then we discussed how that principle was responsible for the failure of Bohr's model. And this is where we left off when we came to a conclusion that there is nothing like exact location or exact velocity in case of an electron. So therefore, the exact location is replaced by the probability density, or the probability of finding an electron at that particular point, and that gave rise to the quantum mechanical model of an atom. Okay, so clubbing this Heisenberg's uncertainty principle with Schrödinger equation gave various solutions to the equations. And we are going to discuss a bit about wave function, specifically about wave function in this video, and then we will discuss how the solution of wave functions led to the definition of all the properties that an electron contains. And then we will finally discuss the quantum numbers and will arrive at a rough structure of an atom. Although this particular branch of chemistry is more theoretical than practical, we have seen until now that initially, the practical was done first and then a theory was arrived, for example, in Rutherford's model. But here, this quantum field of chemistry, or even in physics, this basically deals with theoretical aspects of the chemistry or physics. Okay, so first the theory is arrived, and then the conclusion is confirmed by practical experiments. So we discussed that there is nothing like this fixed orbit in case of an electron. So the electron, we can only say that there is a certain amount of probability that an electron exists at this place. If you find the location of an electron at an instant and you find it to be here, and after some time you find a location of electron at another instant and you find it here, then you wouldn't know, or you cannot know, how this electron came from this position to this position. If you can say that, then it means that you know the exact trajectory of the electron's motion, but that is not possible according to Heisenberg's uncertainty principle. Okay, so therefore just remember that you cannot actually arrive at an exact location in case of an electron. Okay, so moreover, you cannot define a particular trajectory as well. We discussed in our last video that to define a particular trajectory, we need the exact location and the exact velocity, that is magnitude along the direction, in case of an electronic motion. But since to know the exact location and exact velocity simultaneously will be the violation of Heisenberg's uncertainty principle, therefore we cannot just say that the trajectory of an electron is this, as I have drawn it in red color. Okay, so we can just say that the electron can reside in this particular region. Okay, but what will be the exact location of an electron? That we do not. Okay, so now let's move on to discuss the basic aspects of this quantum mechanical model of an electron. Well, one of the main practical reasons for the failure of Bohr's model was that it could not explain splitting of several lines in various spectroscopic experiments. So this particular model precisely predicts why those splitting exist. Okay, so that is basically due to the existence of various subshells that we are going to discuss after some time. So this model, quantum mechanical model. Okay, so Erwin Schrödinger gave us an equation. Erwin Schrodinger, he gave us an equation which looks like this. Now, this particular equation contains all information as far as an electron is concerned. This information contains the electron's velocity. This information contains the electron's probable positions. This equation contains the electronic energy along with the energy of nucleus. This particular equation contains all the information that you need in case of an electronic model or the structure of any atom, along with the nucleus motion as well. Okay. So H here is known as Hamiltonian. It is an operator. H. It is an operator. Okay, called Hamiltonian. Okay, so H is basically, H is the total energy. H is the total energy of an electron. Okay, so it means, since we are talking about the total energy, then it must be kinetic energy plus potential energy. Okay. So now we are going to see what is the value of H and what is the operator. So an operator is a mathematical term which operates on two or more quantities to yield a particular result. For example, the addition that we do, it is also an operator. Or multiplication that we do, it is also an operator. So just like addition and multiplication, Hamiltonian is also an operator. And an operator is just shown with a cap sign over its symbol. Okay, H is Hamiltonian. H is Hamiltonian, and this H cap is Hamiltonian operator. Okay, so this Schrodinger equation looks something like this. Schrodinger equation, it looks like minus H cross square upon 2m del 2 by del x square plus del 2 by del y square plus del 2 by del z square plus v. It depends on x, y, z. Okay. So this is Hamiltonian operator. And psi is wave function. In this case that we discussed, it is a wave function of an electron. Okay. So if we are studying the nucleus of an atom, then we say that psi is the wave function of the nucleus. Since we are discussing the electron of an atom, therefore this is the wave function of an electron in this case. Because what we are trying to figure out is that what is the possible location of an electron, so that we can actually see how does the electron path or electron trajectory may look like. Okay, we cannot know whether this trajectory is exact or not. Okay, so this is the wave function of an electron, and in equation the E term, this is the energy. Okay, so therefore the Schrodinger equation is this. Psi equals E. Okay, where E is the total energy of an electron. Okay, and psi is the wave function. This is Hamiltonian. And now this is the potential energy. And this particular thing is the kinetic energy. H cross is nothing but H upon 2 pi. Okay? And M is mass of an electron. Okay. And now this particular operator is known as partial differential. Okay. So partial differential means that if we are differentiating with respect to x partially, it means that y and z are assumed to be constant in this particular case. In this particular case, we are differentiating with respect to y, so x and z are assumed to be constant. In this case, x and y are assumed to be constant. So therefore, for example, del y del x of x into y into z will be y into z. Okay. So similarly, del y of yz will be xz, or del z of xyz will be xy. Okay. And if it would have been x square yz, then it would have been 2x yz. Okay. So particularly this partial differential works in this way by assuming the other parameters as constant. Okay, so now we are going to discuss a little bit about this wave function because we are interested in this part. Discussing this part is not in the syllabus. So we are not going to discuss what is this, why this is called as kinetic energy, okay, and or how this equation has been derived, or we are not even going to discuss the potential energy as well. So now let's discuss what is this psi. Psi is called as the wave function of an electron. In case of electron, it is the wave function of an electron. It contains all the information of an electron. Okay? By all information, we mean that it contains the probability. It means it predicts the probability of location of an electron, It can give information about magnetic moment, angular momentum, spin, etc. Okay. So wave function has many solutions. This Schrodinger equation has many solutions for wave functions. So each solution corresponds to one particular property of an electron. So since these 2 points I have written in the first point itself, so because since I want to elaborate, therefore I have written these 2 points separately. It contains all informations of an electron, fine, okay. But even though it contains all the informations of an electron, it has no physical meaning. Remember it. It has no physical meaning. Okay, psi has absolutely no physical meaning. Psi is nothing. It is just a wave function which gives us some information about an electron. But psi square has got some meaning. Since by this time you must have studied the complex numbers, therefore I'd like to write here more precisely psi conjugate into psi, which is nothing but the magnitude of psi, absolute value of psi whole square. Okay, so this is the probability of finding an electron at a particular distance. And we define the distance of an electron from the nucleus as r. Okay, so psi square gives us the probability of finding an electron at a particular distance. Remember, in 2013 itself, a question was asked that an equation was given in psi, and it was asked that what will be the probability, at what position the probability of finding an electron will be 0. Okay, so in that case the equation must be solved, and we needed to find the value of psi at which the value of r at which the psi will be 0. Okay, since psi will be 0, it means psi square will also be 0. I think the question was asked in 13, or it may have been in 14 itself. Okay, so we are going to discuss that question later on in one of the videos. So this psi conjugate psi gives us this particular expression, and this is nothing but the probability of finding an electron at a particular distance. Okay, so now I think let's move on further to the discussion of orbitals. We'll again see how this particular psi square gives us the idea about the splitting of orbitals and about the nodes location of various various electrons. We'll discuss about it. So here, since we know that in solar system this is the sun and these are the planets that revolve around sun. In solar system they are in elliptical orbit. It may have been that they are in elliptical orbit. Here, these are suppose the small planets. These are the small planets, and we call this trajectory of these planets as orbits in case of our solar system. But in case of an electron, suppose this is the nucleus. This particular dot is very, very big to be called as nucleus, but still, in order to clarify the things, this particular thing is dot is the nucleus, and the electrons, suppose, are revolving around this nucleus, then this is not a defined orbit. This is not what you say that the electron exists in this particular trajectory, but we call the splitting of this orbit as orbitals. We will study in detail what an orbital is, but still I just want to make you understand through various experiments and of course the solution of Schrodinger equations. After the solution of Schrodinger equation, it was studied that at what points the probability of finding an electron will be significant. Okay, suppose, for example, I am telling you, the probability of finding an electron will be maximum at this region. Suppose, okay. At this region. Fine. And so this whole bunch space is called as orbit, okay, or shelf. Okay. Now, even in this particular space, there are many sub-levels. Okay. There are many sub-levels. For example, some are contained circular shape. Okay. From this nucleus, some, for example, in case of p orbitals, we'll study what a p orbital is. You'll see like this. The probability of finding an electron is maximum in this particular region in case of p orbital. In case of s orbital, the whole circular region is where the probability of finding an electron will be maximum. And in case of d orbital, even if you draw another lobe perpendicular to this particular lobe, then those constitute d orbital. So here, suppose at this particular place, the probability of finding an electron is significant. And also at this place. Okay. Now, this place lies within this orbit. And we call this as orbital. This is orbital. Or subshell. We also call it as subshell. Okay. So, by this example, I hope you clearly understand it, although it is very much difficult to visualize it this way. So, this is called as orbit, this is called as orbital, and there are many types of orbitals. Now we are going to study what those orbitals are, and we are also going to study a little bit about the orbits. But remember here, we made the motion of an electron around the nucleus analogous to the motion of planets around the sun, which is not so. So the orbits in case of planets is entirely different than the orbits that we discussed in case of an electron. Okay. So we cannot precisely define what an orbit is in case of an electron. This was just a rough example to make you understand, and I hope that you have understood it. So, the solution of Schrödinger equation gives us many quantum numbers. We call those integral numbers as quantum numbers. It gives, first is principal quantum number. Principal quantum number. The second that it gives us is azimuthal quantum number. It gives us magnetic quantum number. And it also gives us spin quantum number. Okay? This principal quantum number is denoted by N. Azimuthal quantum number is denoted by L. Magnetic quantum number is denoted by M. Spin quantum number is denoted by S. Okay. So here, principal quantum number, it basically tells us about the size of an electron, size of an atom. Okay. It tells you about energy, that is the state, energy state in which the electron resides. But in case of many electron system, this constitutes the majority of energy and constitutes the majority of energy. In case of hydrogen atom, N constitutes the exact energy. Okay, so principal quantum number gives us the information about the size of an atom and the energy. Okay, so so now, if an electron is in space, for example, just consider the hydrogen atom. The electron has, since the electron is only one in case of hydrogen atom, N equals 1. And in case of ground state, N is always 1. N cannot be greater than 1. N is greater than 1 in case of excited state. So, we are not going to discuss about excited state currently. So, in case of hydrogen atom, N equals 1. So, suppose if this is the nucleus and this is the one principal quantum number, this corresponds to N equals to 1. Okay, so this will tell you how much bigger the atom is. For N equals to 2, it will be somewhat here. For N equals to 3, it will be somewhat here. This is N equals to 2. This is N equals to 3. Okay, so it gives you, or it basically tells you the size of an atom. And also it gives you a lot of information on the energy. Fine. So now this particular N is not fixed. If we say that this N is fixed, then it will be the violation of Heisenberg's uncertainty principle. So this N is not fixed. Now let's just focus our discussion on N equals to 1 in case of hydrogen atom. But first, let's discuss something about azimuthal quantum number as well. Then in that case you will not be actually confused. So azimuthal quantum number for the information, N equals 1, 2, 3, 4 and so on, and its notation is K, L, M, N and so on. Okay, this is the mathematical representation and this is the shell notation. We say that the electron is in shell 1 or shell 2 or shell 3 or shell 4, or we can also say that electron is in K shell, L shell, M shell, N shell. Okay, so now in case of azimuthal quantum numbers, azimuthal quantum number, it gives you an information on the shape. Okay, it gives you the information on shape and also it gives you the information on angular momentum. Okay, for a particular N, for a particular N, its value varies from 0 to N minus 1. Remember, if N equals to 2, therefore, if N equals to 2, then L equals 0, 1. If N equals to 3, L equals 0, 1, 2. Okay, so now you can visualize that if, for example, if this is N equals to 3, then in this case, For n equals to 3, there will be various sub-levels. This is the energy level. Since n is related to electron or electronic energy, and it gives the major portion of energy, then we can also call it as energy level of an electron, in which the electron resides. Now, in this particular level, there are various sub-levels or subshells. N is shell. Electron is in shell 3. So, here, these are the various subshells. You see 3 lines. Okay? So, you can say that for n equals to 3, this is L equals 0, L equals 1, and L equals 2. Okay, so now let's see the notation. In case of L, the notation goes somewhat differently. L equals 0, 1, 2, 3, 4, so on. Notation is 0 for S, 1P, 2D, 3F, 4G, and so on. Okay, and now S stands for sharp, P stands for principal. Remember, this P has got nothing to do with N. Okay, this is also known as principal quantum number. This is the principal value of L. Okay, D is diffused, and F is fundamental, and so on. It goes like this. Okay. So this is going to tell you that this particular electron, the electron for which n equals something, L equals something, has got the particular angular momentum. We're not going to discuss about the expression for angular momentum and so on, because this is not currently in the syllabus. So yeah, we will come back at it again when we'll discuss the shapes of these orbitals. First, let's discuss another two quantum numbers. Okay, so the main quantum numbers that needed to be discussed was this that we have discussed. Now, let's discuss what an orbital is, and that is given by magnetic quantum number. It is represented by M, okay, and its value varies from minus L to plus L. Okay. Now, in this particular L as well, there are various levels or orbitals, okay, of same energy. Okay, and this is M for okay. Now, its value varies from minus L to plus L. Now, in a particular M, 2 electrons exist. So, in a particular 2 electrons exist. Okay. So therefore, for suppose n equals to 2, L equals 0, 1. Okay. we can draw it like this. And m equals, in this case m equals 0, but in this case m equals -1, 0, plus 1. Okay? So, total number of orbitals here are 1, 2, 3, 4. There are 4 orbitals. 1m gives 1 orbital. So, the total number of orbitals here are 4. Okay? So, we draw the orbitals like this. 3 for L equals to 1 and 1 for L equals 0. Okay, this is for L equals 0, this is for L equals 1. This is plus 1, 0, minus 1. Okay? So, now let's discuss the spin quantum number. And in this, we are going to discuss why a particular M contains only 2 electrons. Why not more or less? So here spin quantum number, it gives you the spin state of an electron. Now an electron around a nucleus is spinning, simultaneously revolving, okay, as well. So here while spinning, electrons can spin either in this direction or in that direction. Now these two particular spins, suppose if 2 electrons have got same spins, then they will repel each other. And if 2 electrons have got opposite spins, then they will attract each other, which gives the stability to a particular orbital. Okay. So if this orbital accommodates 1 electron in this spin, this is represented by plus half, that is up spin, or minus half, that is down spin. Okay. Now if this is represented by up spin, then another electron, if it enters in this orbital, cannot exist in up spin, because if they do, then they will repel each other, hence leaving the orbital unstable. Therefore they cannot exist together. Hence the another electrons will have to exist with opposite spins, so that they can attract each other and hence binding an electron. Binding each other, thus providing stability to the orbital. Now, the third electron cannot enter in this orbital again, because if it does, then again these 2 electrons will repel each other, again the orbital will be unstable, and hence one orbital can accommodate only 2 electrons. Okay. Now in this case, one orbital accommodates 1 electron, this again, then the 4th electron gets paired up like this. We call this pairing of electrons. When 2 electrons of opposite spin approach each other and occupy an orbital, we call it pairing of electrons. Now, why have we filled the electrons in this manner? We are going to discuss after some time in Hund's rule. Okay, so here now why we have written this orbital separately and these 2 orbitals separately? Because this orbital is of particular energy and this orbital is of different energy than this one. But these 3 orbitals have got same energy. So the orbitals with same energy are degenerate. Orbitals of same energy are degenerate. Okay. So if any 2 orbitals have got same energy, then we say that the orbitals are degenerate. Okay, they have the same energy. Now, here in this case, 3 orbitals are degenerated. But remember, in case of hydrogen atom, in case of hydrogen atom, 2s and 2p have same energy. Okay, so remember, in this case, energy depends on N only. But in multi-electronic species, energy depends on N as well as L. Therefore, the energy is a function of principal quantum number as well as azimuthal quantum number, because azimuthal quantum number tells you about the angular momentum of an electron, and since angular momentum of an electron also has some energy, although the major part of the energy will be represented with N, but N also has some energy. So we'll see how the energy of one species is smaller and the energy of one species is greater after some time. So here, now let's discuss about the shapes of the azimuthal quantum number that we discussed. At first, let's make note of the fact that an electron in a particular orbital is represented with, or an electron is represented as an electron in a particular orbital is represented as N L and N into L into X, where X is the total number of electrons. Okay, N is principal quantum number, L is azimuthal quantum number. For example, 1s2 or 2p6. It gives us that this electron resides in the principal quantum number 2, azimuthal quantum number 1, p, because p corresponds to 1, and it has 6 electrons. And 6 is the maximum number of electrons that can be occupied in 2p subshell. So, let's discuss an example of the total number of electrons that can be accommodated in quantum number N, principal quantum number 3. Okay. So here, suppose if the question says calculate maximum number of electrons in or having principal quantum number N equals 3. Okay, so we are going to approach this question by making a chart to in order to make you understand. So here N equals 3. It means L equals 0, 1, 2. Okay. For this, m equals 0. For this, m equals -1, 0, plus 1. And for this, m equals -2, 0, or -2, -1, 0, plus 1, plus 2. So there are in total 5 plus 3 plus 1, that is 9 orbitals. So total 9 orbitals. Okay? So therefore, total number of electrons equals 9 into 2, that is 18. Because one orbital can, because maximum 2 electrons can be accommodated in a particular orbital. Okay, so we can represent it like this. Okay, so the total number of electrons are 10 plus 6, that is 16, plus 2, 18. Okay, so now you can be asked that how many electrons can be there for which principal quantum number is 3 and spin quantum number is plus half. So in that case, the total number of electrons will be 9, because here there are electrons which have spin as plus half and minus half, and both are in equal number. Okay, so only these electrons will be counted. Okay, that is the electrons which have up spin, that is half. So in this case, it will be 9. Or you can be asked, what can be the total number of electrons or maximum number of electrons for which n equals to 3, l equals to 2 and s equals to plus half. So in that case, we are going to consider only these number of electrons. So the answer is 5. Okay. So there can be different variations of this particular problem. Okay. So I'll stop here. In our next video, we are going to discuss the shapes of an orbital, and we are also going to discuss the probability of an electron, or the places at which the probability of finding an electron will be 0. We call them nodes. So what are nodes, or how can we calculate the position of nodes? Okay, so we are going to discuss it in next video.